So let's look at this idea of the Pythagorean trig identities. Because basically it comes from our unit circle there. The equation which being x squared plus y squared is 1. But any point on there can have coordinates of an x value of cos theta and a y value of sine theta. It's what's actually known as the parametric coordinates of a circle. But that doesn't matter for us, because all we need to know is we know x squared plus y squared is equal to 1. It's very easy to prove x would equal cos theta, y would equal sine theta. That gives us our first Pythagorean trig identity. So the reason they're called Pythagorean trig identities, it basically came from Pythagoras' theorem. So sine squared plus cos squared equals 1. Now some people say there is only one Pythagorean trig identity, and that's it. Because to get the other two that we're used to seeing, it's just a little bit of manipulation. If I divide everything by sine squared, well then I get sine squared on sine squared, which is 1. Cos squared on sine squared, which is cotan squared. And 1 on sine squared, which is cosec squared. And we often quote that as another trig identity. But imagine I divide it instead by cos squared instead of sine squared. Then sine squared on cos squared, well that would be tan squared. Cos squared on cos squared, well that's 1, and 1 on cos squared is x squared. And that's often quoted as the third trig identity. But as I say, really, all three are the same. It's just a rearrangement of writing it. There is one more relationship whenever we're proving these sorts of questions that comes in real handy, and that is that relationship right there. The ratio of tan theta being sine theta on cos theta. That can come in useful when we're proving these sort of identity questions. Now, the first question I put up is a question that people always associate with the trig identities, and I'm going to say to you, that's a waste of time. Exactly, I saw someone saying exactly right, just draw the triangle. That's what I would do too. But I think the reason they put in this exercise is because what they do is they say, oh well, if cos theta is 3/4, you could sub it into sine squared plus cos squared equals 1, and then you could work out what sine theta is. But I agree, it's much easier just to draw the triangle. Well, cos theta is 3/4, bit of Pythagoras, root 7. I'm told tan theta is negative. Cos theta is positive, therefore I'm in the fourth quadrant, so sine must be negative, and I just read off my triangle, and we get minus root 7 on 4. That to me is the more efficient way of doing it. Alright, well let's actually look at some of these trig identity questions. Simplify 1 minus cos squared, and it is a rather straightforward one, but let's just imagine for a second I don't see it straight away. How would I approach it? I'd go, 1 minus cos squared. Well, which trig identity involves cos squared? And that's the one that says sine squared plus cos squared is equal to 1. So I could rewrite that and say cos squared is 1 minus sine squared, and expand on, what do you know, I just get sine squared. Now, of course, I'm not expecting people to do it that way. I would hope you see 1 minus cos squared and recognise it straight away and go, oh, well, that's sine squared. But whenever in doubt, the nice thing about the trig identities is they all involve different ratios. So you just got to think, hey, which one of the identities am I going to use? Rearrange it, sub it in, and it usually comes out. So if I had, there we go, similar deal. Sec squared minus tan squared is one of those ones that after a while, hopefully we recognise straight away. But just say we didn't, what involves sec squared, what involves tan squared? Hang on, I know sec squared is 1 plus tan squared, so how about I just substitute in for sec squared, and what do you know, tan squared minus tan squared disappears, and we get 1. Tan theta cos theta, hang on, there's no squares there. Oh, maybe this is one where I'll use the useful relationship. Well, tan theta is the same as sine on cos. Oh, there you go. The cos cancels and we get sine. These are the more interesting questions where we have to prove a result. So 2 sec squared alpha minus 2 on 4 tan alpha is tan alpha on 2. Now, when you do these, here we go, it's up to you how you want to approach it. There's nothing that says you have to start with the left-hand side. I have in this case, but you could just as easily start with the right-hand side, manipulate that if you wanted to. It's up to you how you do it. I've chosen the left-hand side because it's got the sec squared in it, which is a trig identity. So I know I've got something I can play around with. 2 sec squared minus 2, again, I could say, well, hang on, I know sec squared is 1 plus tan squared. substitute in, tidying that up. Hang on, 2 minus 2, that disappears. Oh, hang on. 2 tan squared on 4 tan. Tans cancel. 2 on 4 cancels. I've got my tan alpha on 2. Okay. Now, the thing about these proof questions and show questions where you're given the answer, you don't want to make it look like you've just fudged the answer and gone, oh, well, I know what the answer is going to be, therefore this line must do this. So sometimes you do write substitution steps in that you might not normally do because you're doing it in your head, but you need to be able to show how you got the answer. Whether you do it like I've done or maybe to the side, write your reasonings like you do in geometry. Like you might substitute straight in and say, oh, well, I can do that because I know sec squared is equal to 1 plus tan squared or something like that. But basically, when you're doing a trig identity, it is a proof. So you can start with the left-hand side and then go and prove the right-hand side. You can start with the right-hand side, prove the left-hand side. Of course, the third option is start with whichever side you like. You might get to a point and go and get stuck, and you go, oh, hang on, I'm not sure how this is going. I'll just put that to the side for now. Let's go play with the right-hand side. And then you go and play with that, and if all of a sudden you go, hang on, I've just shown the same line as I did over here, brilliant. Because if I've now shown they're both equal to something else, some third thing, I can then conclude, well, they've got to be equal. So that's the one we do. Never solve like an equation. It's not an equation. Because an equation is saying, find the values for which this is true. We're proving it doesn't matter what you substitute in, it's always true. So we're not solving an equation. So let's play with trig identities. So I guess work on the setting out, your proof. Someone should be able to read your proof and understand it. Yes, of course. So if you need to write explanations down, you write explanations down.